Okay, then let us start. So in the last class, we started with the idea of measure, right? Measure space, right? So what is a measure space? Measure space is a triple, right? It contains three things. One is a set, and then a collection of subsets of that set uh, satisfying some conditions. Right? That is called sigma algebra, right? And then we define something called a measure, right, on the sigma algebra, right? So this triple is called a measure space, right? So I described that because what we are learning in this course about the probability and probability theory can also uh, looked at as a measure space and measure theory, right? Here we are talking about a special kind of measure, right? So after describing about those words, I came to the probability theory special class of measure spaces, right? So there what we have is the initial set in this situation is the sample space, right? So we defined several words before that. Statistical experiment is any action or a process of actions generating some observations, data, right? And then we learned the word sample space, that is set of all possible outcomes. Before that, the word outcome is one single result coming from one experiment is an outcome. Of course, an outcome can be a single entity or it can be several entities, right? But it is considered as one result, right? And then sample space, and then based on the sample space we talked about a particular sigma algebra, right, that we usually talk about. In that case we saw that if the sample space is finite, usually in elementary level, and usually the sigma algebra that we consider is the power set, right? So we define an event to be an element of the power set generally, but there can be special situations where the sigma algebra that we are interested in may not be the whole power set, but instead of that, some other set which may not include all the elements in the power set. So we looked at an example in the last class, but that is very rare. But usually we can define in the case that the sample space is countable. Usually we take the power set as the sigma algebra that we are interested in. So when you say countable, it can be finite, right? Countably finite or countably infinite, but countable, right? The other case is sometimes we are dealing with sample spaces which are not countable. For example, a set of real numbers or maybe a subset of real numbers, that set is not countable. In that kind of situations, we usually don't talk about the power set, because the power set contains in that case uh, unimaginably large number of sets, and we are not interested in all of those sets. We are going to be interested in some particular type of sets only. Therefore, usually it is more than enough for us to consider when for example your sample space is R or a subset of R. It's usually enough to consider the Borel set, that is set of uh, open sets coming from the real line, right? So usually, therefore, when your sample space is uncountable, we consider the Borel set as the sigma algebra, right? So we define events based on the sigma algebra always. That's what we discussed in the last class. So we looked at some examples. So I think we don't need to go through all the examples again. I just remind you the words here. So we looked at all these examples in the last class. So I think this is where we stopped, right? So I have to continue from here, right? So this is the place where we define the measure, right? So we have talked about the set, that is the sample space. And generally, if the sample space is countable, then the sigma algebra that we consider is the power set, otherwise the Borel set. So based on the sigma algebra that we have selected, now we want to talk about the measure, right? Especially in this case, the probability measure, right? So probability measure is a kind of a measure that has the properties of a measure, right? We have given some properties. What are the properties that a measure should satisfy? Hmm. Okay, let's go back. Yeah. So this is right. So for example, we define a measure from the sigma algebra to the positive or non-negative real line, right? Zero can be included. And it is actually the extended real line. Infinity is also included, right? So we define a measure from the sigma algebra from 0 to infinity, including those two. So any function m, right? So here I denote the measure by m. Any function m satisfying these conditions is called a measure, right? So if you apply, we know that if you a is any element of the sigma algebra, always when you talk about the measure of that element or measure of that set, it has to be greater than or equal to 0. That means it cannot be it cannot be negative, right? Always 0 or positive. And then the second one is, of course, the null, not the null set. Empty set is always a member of the sigma algebra. So by definition, when you apply the measure on the empty set, the answer should be 0. That is another requirement. And the other thing is countable additivity. That means if you consider a union of sets in the sigma algebra, and if you apply the measure on that union, that should be equal to the sum of the individual measures on the individual events. Not generally, not necessarily events in this case, subsets, right? So that's what we mean by the countable additivity, right? If you apply the measure on a union of sets where these AIs are coming from the sigma algebra, then that should be equal to the sum of the sum of the measures of individual sets, right? So if some kind of function satisfies those properties, that's called a measure. But when you talk about the probability measure, all these have to be satisfied. But in addition to that, we have a special one more requirement, that is the measure when we apply on uh, the whole set, right? If, for example, omega is the sample space, any sigma algebra must include that set also, right? Any sigma algebra must include the empty set as well as the original set. So the requirement here for the probability measure is, in addition to these requirements, when you apply the measure, in this case the measure I denote by PR. Instead of M, I use PR because that's what the book is using for the probability. So that is an additional uh, restriction that we have put. If in addition to the previous ones, if the probability of the sample space or the measure of the sample space is equal to 1, then that kind of measure is called a probability measure. Right? Generally, it can be a measure with the previous ones, but in addition to that, if the measure, when you apply the measure on the whole set, if you get 1, so that becomes a probability measure, right? That is just another name. So here you consider the sample space and then whatever the sigma algebra you are looking at, and then the probability measure. This triple is called a probability probability space. It's like measure space. Now it's a probability space, right? So let's look at some examples of probability measures, right? When we talk about calculation of probability in the university or A levels also you have discussed this. You are just considering how to calculate probability, right? This is how to calculate probability, right? So you have discussed several methods, several methods, right? But now in this case, we can call them probability measures. One method is using some equation to calculate probability. So that equation or the formula actually gives you a probability measure. That measure satisfies all those conditions, right? So one method is, you already know, the classical method, right? Classical method to calculate the probability, right? So up to now, from what you know, I think you know that you can use the classical method to calculate the probability of an event under certain conditions, right? What are the required conditions? If, for example, E is an event, right? So that means E is an element of some sigma algebra coming from the sample space omega. Then you can calculate the probability of, or measure the event E in terms of probability if the sample space is finite. That is the first requirement. The sample space must be finite. And the second requirement is all the outcomes in that sample space should be equally likely. Right? If those two conditions are satisfied, then you already know that you can use the classical method to calculate the probability of any event. Right? So this is this is what I have mentioned here, little bit more mathematically. So suppose you have some sample space with some finite number of outcomes. Let's denote the outcomes by omega 1, omega 2 up to omega n. So n is a finite number. And let us consider, as generally what we do, we just consider the power set as the sigma algebra. So let's consider our sigma algebra to be with the power set and assume, or maybe suppose, for example, we can assume, right? We cannot always assume. Suppose it is reasonable to assume that outcomes are equally likely, right? So it gives you a problem sometimes, because some students have difficulty in deciding whether it is reasonable to assume outcomes are equally likely or not, right? Because one reason for that is actually equally likely. The word equally likely itself contains the idea of probability, right? So if you want to talk about probability using some similar words to probability, is kind of a circular definition, right? But this has to be a feeling. Like, for example, there should be you should be able to think whether there is any reason for the outcomes to be not equally likely, right? Whether there is any reason for some outcomes are more likely than the other one, right? If that is the case, if you feel like that for some reason, then that is not, of course, an equally likely outcome. Sample space, right? So in order to make sure that outcomes are equally likely in modeling, sometimes we talk about fair coin, fair die, and so on. That we include the word fair to make sure that outcomes are equally likely. But in practical situations, you don't have to use fair always. You can think sometimes whether one is possible. Outcomes are equally likely or not. We will look at some examples anyway. So suppose sample space is finite and the outcomes are equally likely, then the probability of any event coming from this sigma algebra can be found using this formula, right? So here, this absolute A means actually the size of A, size of the event. By size of the event, what we mean is the number of outcomes in that event A, number of outcomes, right, divided by the size of the sample space. That is again the number of outcomes in the sample space. So in the elementary level, that's how we define the probability of the event A is equal to number of outcomes in event A divided by number of outcomes in omega, sample space, right? So if the number of outcomes is n, this will be n. So that is the definition. And so this is a function. This is a function defined from the sigma algebra to a 0, 1 interval. If you calculate this number, always this number is going to be between 0 and 1, because this number is always less than this number, less than or equal, right? So therefore, so that property is there. In addition to that, you can prove that all the other conditions that a general measure should satisfy are also satisfied by this function. So therefore, this is a measure by definition, and that measure is called a probability measure. This particular measure has a particular name because as we know, the method is called classical method. Therefore, we can call it, I don't know whether everybody calls it like that, but we can call that measure a classical probability measure. It's a classical probability measure, right? Oh, that's classical probability method at the beginning, right? So that is one example of a probability measure. Let's look at another one. So there are lots of situations where that requirement for us to use to calculate the classical probability are not satisfied, right? There can be, maybe the sample space is finite, but the outcomes are not equally likely. It's not reasonable to assume that the outcomes are equally likely. For example, suppose you have a coin. Generally, we don't know whether the coin head and tail are equally likely or not, unless we assume that it is fair, right? So even in that case, a very simple case, if one asks what is the probability of a head, we cannot directly say it's 0.5. We cannot say that. We don't know, right? Unless somebody tells us that it is fair. Right? So suppose you have a situation like that, right? How do you find out the probability? So for that kind of situations or any other situations where you cannot assume the outcomes are equally likely, then you may use this method. So this is the second method. Again, many people know, we call it the relative frequency method. Relative frequency. In relative frequency, the idea is the event that you are looking at, actually the event that you want to find out the probability must come from something called a random experiment. A random experiment is an experiment which can be repeated again and again and again under the same conditions, right? For some experiment which is not random, we cannot talk about this one, because in order to talk about this one, we say, okay, suppose you repeat this experiment again and again and again large number of times, and then each time each time you do the experiment, either your event occurs or your event doesn't occur, right? ඕනම වෙලාවක තමන් එක්ස්පෙරිමන්ට් එකක් කරපුවාම තමන්ගේ ඉවෙන්ට් එක එක්ක සිද්ධ වෙනවා එක්ක සිද්ධ වෙන්නේ. අපි ඒක තමයි වෙන්නේ. Right? So suppose you do it once, you do the experiment once and see whether your event occurs or not. If it occurs, we say, okay, we put a 1. Otherwise, we record a 0. Right? Do the experiment again, see whether your event occurs or not. Right? If the event occurs, then record another 1, otherwise 0, like that. So records ones and zeros accordingly, doing the experiment again and again and again as many times you want, right? And then if you add the numbers ones and zeros, what do you get? You get the number of times that your event occurred, right? And if you divide that, so that is the frequency of your event up to that point. If you divide that number by the total number of times you did the experiment, then you get the relative frequency of that event, right? How many times or proportion of times that event occurred, right? Relative frequency is the same as the proportion of times, right? So by definition, now here, if you generally assume that you have done the experiment n times, you will have a relative frequency when n is equal to 1, right? In that case, always the answer is either 1 or 0. පළවෙනි අවස්ථාවේදී 1 or 0 නෙන්නේ. මොකද සිද්ධ වුණා නම් එක අපි රෙකෝඩ් කරන්නේ කරපු වාර ගාන එකයි, එක බෙදීම එක එකයි. පළවෙනි වාරේදී උනේ නැත්තම් අපි රෙකෝඩ් කරන්නේ බිඳුව, අරක එකෙන් බෙදපුවාම බිඳුව. ඔය දෙකෙන් එකක් තමයි පළවෙනි වාරේ අනිවාර්යයෙන්ම relative frequency එකට එන්නේ. So we will call it F1, for example. Frequency is f, and then if you divide that by 1, relative frequency in the first step. Like that, at the nth step, you have a relative frequency. So if you let this n go to infinity mathematically, right, then usually this sequence of relative frequencies converge to some number, right? Usually this converges to some number. So we define that number to which this sequence of relative frequencies converge as the probability of the event, right? That is what the definition, relative frequency definition, is defined as a limit. The limit of the relative sequence of relative frequencies as n goes to infinity. ඒක තමයි definition එක. ඒක තමයි මෙතන මේ ලියලා තියෙන ටිකක් mathematics පාවිච්චි කරලා මේ ලියලා තියෙනෙත් ඒකම තමයි. හැබැයි මෙතන තියෙන තාම limit එක ගැන කතා කරලා නැහැ. Here we are still first considering the situation at the nth step, right? At the nth step. So the nth step එකේ තියෙන්නේ මෙතන තියෙන්නේ PNA කියලා දක්වලා තියෙන්නේ some measure Pn like m. Here මෙතන Pn වලින් දක්වලා තියෙනවා. ඒ කියන්නේ n වෙනි අවස්ථාවේ කියන එක දක්වන්න. Right? So Pn is a function evaluated at A. This is how we evaluate it. So this gives you the number of times that event occurred up to the nth experiment and then divided by n. So that's actually the relative frequency at the nth trial. Right. So ඒක බැලුවත් අපිට මේ PNA කියන එකත් ඒකත් හැමතිස්සෙම බිඳුව සහ එක අතර තියෙනවා. ඔයගේ හැමතිස්සෙම බිඳුව සහ එක අතර තියෙනවා. ඊට පස්සේ ඔය ෆන්ක්ෂන් එකත් Pn කියන ෆන්ක්ෂන් එකත් අර කන්ඩිෂන්ස් ඔක්කොම සැටිස්ෆයි කරනවා. measure එකක් satisfy කළ යුතු සියලුම conditions satisfy වෙනවා. So this itself is a probability measure. මේකත් probability measure එකක්. Right? Actually that is what practically we use. Right? We use this thing with a large n. Right? Usually for small n this is not giving you a good measure, but it's a measure anyway. Mathematically it's a measure. Right? Even for n equal to 2 it's a measure. P1 we don't consider is because it's trivial one, but P2 can be considered to somebody, but that P2 will be a measure, one function. P3 will be another measure. P4 will be another measure. Everything is a measure, right? But those are not good measures as far as the probability is concerned. And now what we can do is we can consider the limit also. What happens to n when n goes to infinity, right? So it's a limit of a sequence. So it might exist or not exist. If it exists, then we define it as the probability, actual probability of the event. Right. So that function, the limit, is also a measure. It's a different measure. So that can be we can show that it's again between 0 and 1, inclusive those numbers, and the other properties are also satisfied. So what a Pn for a given n is a probability measure. Right? It's a probability measure. We can call it empirical probability measure. Empirical probability measure. Right? And then right? If you let n go to infinity, if that limit exists, right, then this is the definition of the probability. Actual probability of A is defined as the limit of P and A as n goes to infinity when it exists. So this function, that's what we denote by PR here, is a probability measure, and we can call it relative frequency probability measure. Relative frequency probability measure. Previous ones also යම්කිසි ආකාරයක probability measures තමයි. Right? So ඔය දෙකේ නම් ඕම් පාවිච්චි කරනවම කියලා පොත්වල නැහැ. මම නිකන් දැම්මේ නම් අවශ්‍ය නැහැ අපිට. ඒකේ හැම එකටම නම් අවශ්‍ය නැහැ. නම් නැති measures ඕන තරම් තියෙන්න පුළුවන්. Right. So that is an example. Actually, this is the measure that we usually use. Pn is the measure that we usually use in most of the situations. We are using Pn, this measure, as our probability measure with a large n, right? So we have to have data from large number of experiments, where the large can be different from situation to situation. But if you can do it as many times you want, then you can be happy that your probability that you are getting will be very close to the limit, and therefore whatever you are getting will be very close to the actual probability. Right. So here I produce some graphs to show you that what happens actually if you increase n, right? So here I generated data, for example, assuming that I'm tossing a fair coin, for example. So I'm considering one of the events, a head or tail, with a probability 0.5, right? So if I do that, what you can see here is actually 100 sequences, not one sequence, right? So, so at the beginning, always it starts with 1 or 0, right? And then after that, the relative frequencies are converging like this. I have done the experiment 10,000 times, 10,000 times using the computer. Right? This is a simulation using R. We can write down functions later on to do, produce this kind of graphs. So you can see that actually you cannot see individual lines here. මෙතන 100ක් තියෙනවා ඒ වගේවා. මොකක් හරි එකක් තෝරගත්තොත් එක පාටක් අපිට තෝරගන්න පුළුවන් නම් ඒකෙන් දක්වනවා ඒ අවස්ථාවේදී කොහොමද relative frequency එක වෙනස් වුනේ කියලා. ඊට පස්සේ වෙන පාටක් තෝරගත්තොත් ආයසරයක් ඒ අවස්ථාවේදී කොහොමද දිගට ඉස්සරහට යනකොට relative frequency වෙනස් වුනේ කියලා. ඒ හැමතිස්සෙම you can see always it's converge into something. Actually, when I selected the fair coin situation, we can see that the relative frequency was converging to 0.5 here. This is 0.4, this is 0.6, this is 0.5. So you can see that it's converging to 0.5. Because you cannot see it very clearly, what I did was I took the last 100 points here from 9,900 to 10,000. And if you make it little large, this is the end, this part here, magnified. So you can see that they are all very close to 0.5. This is 0.5, this is 0.51, right? This is 0.485, right? So in addition to that, you can see that most of the relative frequencies when n is very large are going to be very close to 0.5 here, very close. Only few are a little bit away, but still they are very close, between 0.1 or so, 0.01. Right. So that's what we mean by practically converging to a particular value. If I did it maybe 100,000 times, you will see that it's almost coming to 0.5. So this is another one I did with another value of, so for example, I created an event with probability 0.2, right? So I did that experiment again and again and again. And in that case, you can see the relative frequencies converging to 0.2 here. Right? Earlier, my event had probability 0.5. Now, I created the same procedure, but now I changed the probability. So I know the probability at the beginning. So when you do that, you get this kind of graph. Again, you can see that large number out of these 100 simulations, large number of simulations are very close to 0.2, this 0.205, 0.195, right? About 95% of those are within very close interval. So that's what we mean by converging. And actually, in the last class, somebody asked me about this mathematical question about the convergence. When we talk about this kind of convergences, actually there are several modes of convergence. Several modes of convergence, right? There's something called almost sure convergence. Another one called converging in probability, convergence in probability, which is the same as the weak convergence, right? So here, actually, this convergence is an almost sure convergence, and mathematically, this is how we define the almost sure convergence. Right. මෙතනදී මේක දැම්මට මෙතනදී here I'm using some idea that we have not discussed yet, some idea about the random variable. Right. තාම random variable ගැන කතා කරමු නැති හින්දා මම ඒක දැම්මට මම මෙතනදී මේක කතා කරන්න යන්නේ නැහැ. If I want, I will come back, because here I have used the idea of a random variable to explain this. You need a random variable to explain this, but up to now we have not discussed the random variable. So I will come back to this thing a little later. If you want me to explain that, right? There are definitions and what we mean by almost sure convergence and so on, right? So now we have discussed two methods, right? Classical method and the relative frequency method. In addition to that, another method is actually the modeling method, probability models. We use probability models to calculate probabilities of events. So this modeling in the previous situation also, if you are doing it only up to a certain n, right? Of course, you cannot do it infinitely many times. No, you cannot repeat your experiment infinitely many times to see where it is converging to. So that's impossible. So practically what we do is we do our experiment as large number of times as we can, and then use at the end the relative frequency as an estimate for the actual probability. So that's an estimate. Always there is a error. There's an error. That means there's a difference between the actual value and the estimate. What happens is that estimate, the size of the estimate comes close to 0 and 0 with high probability. The third method is again modeling. In the modeling also, we have to make some assumptions. There are some assumptions always in modeling, right? So under those assumptions, we write down some mathematical model for the probability measure. We use some mathematical model, mathematical equation for that PR function, probability function, right? So there are so many models that we can talk about. We usually call them probability distributions, and we will talk about those little later. But in general, I have given you one example here. Suppose you have a sample space which contains 0, 1 up to n. Right? So actually this happens usually. For example, suppose you toss a coin 10 times, right? So if you look at the number of heads in these 10 tosses, your outcome can be 0, 1, 2, 3, 4 up to 10. Number of heads in 10 tosses. That is, so 10 tosses is one experiment. 10 tosses is one experiment. So do the 10 and then see how many heads. So that can be 0. So 0 is a possibility. If you do it again 10 times, toss the coin 10 times, in that case, maybe you get 5 heads. So in that case, outcome is 5. Right? So like that, 0 to n, right? If you do it n times, 0 to n are possible values. So generally, again, because this is a countable set, naturally we would use the power set as our sigma algebra. So if you define the probability of getting any of these numbers by this equation here, and then if you define the probability of any event A will have some will be a subset of this thing, no? Any event A is a subset of this. So the probability of A, if you define like this, sum of the values coming from this function taken as the probability, then we can show that this function defined like this with pi given by this equation has this probability measure properties. That means it gives you always a value between 0 and 1, and the other properties are also satisfied, right? So this is therefore, if you define the probability of a set like this using this equation with pi given by this, then that's a probability measure. So that's actually a model. We call it the binomial model, right? So this formula here is called the probability mass function of a binomial random variable. We will talk about those things in detail a little later. But here at the moment, I am showing only some examples of probability measures, right? So the probability is defined like this with the help of this model here. And here at the last, I am considering an example where you have for example, uncountable sample space. Suppose your sample space is set of real numbers. In that case, as I mentioned earlier, usually we don't consider the power set as the sigma algebra. We consider the Borel set as the sigma algebra. So therefore, this will be your sample space and this will be your sigma algebra. So that's a measurable space. And suppose you can define a measure, probability measure on that by something like this. Right? So the probability of some event A coming from this Borel set, where A is a Borel set, can be given something using some integration of some function. Right? So here this function is like pi in the previous example. That was some function, and there we wanted to add that function to get the probability of the event. In this case, we are integrating some function to get the probability of event. Right? So we can show that if you define, if you consider this function, this always this value will be between 0 and 1, and this function also satisfies the properties of the measures. Therefore, it's a probability measure. And in particular, this thing here is called, we will later on learn about that. It's called the probability density function of a standard normal distribution. So we use this particular standard normal model in some situations. So if you think that that model is suitable for your problem, then we can use this probability measure to calculate the probability of any event in the related to your problem. Right. So therefore, we should learn some models where in different situations we can choose a suitable model, and then based on that we define the probability measure or calculate the probability. Right. So therefore, in different situations, the probability measure can be different. Only thing is that all those measures should satisfy the required conditions. And this is another one called conditional probability measure. The when we learn this thing in the A levels, we don't call it a different measure. It's a different section in probability theory. Right? We were talking about unconditional probability earlier. Right? For example, if you are rolling say if you are rolling a die, we may be interested in what is the probability of getting a number less than 4. You can calculate that probability. Right? One might ask, I have seen what we got. I know that the number we got is an even number. What is the probability that the number is less than 4? So in that case, I am asking about, given that I know that the event happened was an even number, so now what is the probability that the number is less than 4? So that kind of probabilities in general we call it conditional probability. Conditional probability of getting a number less than 4 given that or knowing that or if the number is an even number. So that's what you mean by a conditional probability. So a conditional probability කියන එකත් අපි define කරන්නේ මේ විදියට. This is how you define the probability of some event A given that you know that B has happened, or conditional probability of A knowing that B has already happened, or the conditional probability of event A if B happens. Right? In all these situations, we use this thing. This is the way that we have defined that one. This is some original probability measure, probability of A intersection B divided by probability of B. Of course, in order for this to be meaningful, probability of B should not be equal to 0. Right? This is not defined if the probability B is equal to 0, and let us denote this the probability given by this thing by PBA, P subscript BA. අලුත් probability measure එක. Right? මෙතෙන්දී අදහස් කරන්නේ probability of A given this event. Probability of A given this event. Right? එතකොට ওই විදිහට අපි define කරොත් මෙන්න මේකත් මේ PB කියන එක function එකක් හේවලා. PB is a function. And we can show that PB is always whatever you got whenever you evaluate PB at some event in the sigma algebra, always you get a value between 0 and 1. And PB function also satisfies the properties of a measure, and therefore PB itself is a probability measure. PB is also a probability measure. Right? ඒක වෙනම probability function එකක්. Right? එතකොට අපිට පෙන්වන්න පුළුවන් probability of P when you evaluate PB on set B, actually the answer is 1. එතකොට අපි කලින් දන්නවා සාමාන්‍ය probability වලදී PR දාපුවාම PR of omega is equal to 1. sample space එකේ probability එක තමයි 1 වෙන්නේ. නමුත් මේකෙදී අපිට පෙන්වන්න පුළුවන් probability if you apply this function on B, B කියන්නේ subset එකක්. ඒ subset එකේ probability එක මේ probability measure එකට අනුව 1 වෙනවා. හරි. ඒකේ මෙතන කියන්නේ මේ okay, let me use the board a little bit. Suppose you have a certain sample space you may have several events, right? Suppose this is your B event here, and this is A, right? So if you consider the probability P, B, A, right? Make P, B, A is defined as the probability of A intersection B divided by probability of B, given that probability of B not equal to 0. Right. එතකොට දැන් මෙතෙන්ට B දැම්මොත් මොකද්ද වෙන්නේ? Probability B is the function. This B here is probability of B intersection B divided by probability of B. Right. So B intersection B is again B. Right. So therefore this is probability of B divided by probability of B. So that is 1. Right. ඇයි ඒක වෙන්නේ? ඒ කියන්නේ given that B has occurred, the probability of B occurring is 1 නේ. B වෙලා කියලා දන්නවා නම් දැනටමත් එහෙනම් probability B සිදුවීමේ සම්භාවිතය එකයිනේ, අනිවාර්යයෙන්ම මේක වෙලා ඉවරයිනේ. ඉතින් ඒක හැම වෙන්න ඕනනේ. ඒ කියන්නේ මොකද්ද කියන්නේ? අපි දැන් මෙතනදී සාමාන්‍යයෙන් අපි probability හොයනකොට sample space එකට සාපේක්ෂව තමයි probabilities calculate කරන්නේ. අර මෙතන මේ PR කියලා තියෙන එක sample space එකට සාපේක්ෂව තමයි අපි තියෙන්නේ. කො වෙලාවක. right sample space එකට සාපේක්ෂව. නමුත් දැන් මෙතන හොයනකොට මෙන්න මේ හොයන්නේ මොකද්ද? probability of A given B. එතකොට අපේ sample space එක මෙන්න මේක බවට පත් වෙනවා. දැන් අපි දන්නවා B සිද්ධ වෙලා තියෙන්නේ already. ඒතර අනිත් ඒවා වෙන්න දෙයක් නැහැ. එහෙනම් B සිද්ධ වෙලා තියෙන්නේ. ඒක වුණා කියලා දන්න වෙලාවට A සිදුවීමේ සම්භාවිතය හොයන්න නම් මෙන්න මේ කැලේ සම්භාවිතය තමයි හොයන්නේ. So that means in this situation B becomes the sample space. B becomes the sample space. එතකොට එහෙමනම් A sample space එකේ A probability එකට සාපේක්ෂව B වල සම්භාවිතාව එක වෙන්නත් ඕන. ඔරිජිනල් එකට අපි දන්නවා B probability කියන ෆන්ක්ෂන් එකේ ඒක ඉවැලුවේට් කරපුවාම ඔමේගා ගේ එකයි වගේම B කියන ෆන්ක්ෂන් එක B මත ඉවැලුවේට් කරපුවාම එක වෙන්නත් ඕන. එතකොට mathematically අපිට මේ වගේ පෙන්වන්න පුළුවන්. We should get the idea also why we are getting like that. Right. So once you say that some event has occurred, your sample space becomes that set. You are now talking about relative to that event. Right. Do we have an eraser? Right. Anyway, remember that in general, in almost all books, we don't write down, we don't use this notation. මොන පොතකවත් conditional probability එකට ඔය PB කියන notation එක දාන්නේ නැහැ. ඒගොල්ලෝ තවමත් පාවිච්චි කරන්නේ PR කියන notation එකම තමයි. ඒගොල්ලෝ ඒක ලියන්නේ PR of A given B. This is the way that people usually write down. Right? Right. Thank you. නමුත් මතක තියාගන්න ඕන එක දෙයක් තමයි මෙතන PR කියන එකයි මෙතන PR කියන එකයි දෙකම සමාන නැහැ. ඒ දෙකම එකම නෙමෙයි. මෙතන PR වලින් මෙතන මේ මෙහෙම දක්වලා තියෙන්නේ ඇත්තටම මෙන්න මේක. තමයි එහෙම දක්වලා තියෙන්නේ. ඒතකොට මේ PR එකයි මේ PR එකයි සමාන නැහැ. එහෙම පොත්වල ලියුවා. So that's something that many people don't know. And it's not explained like that also. So this PB itself is a probability function, but usually we don't, in books we don't write down like that. We write down like that A probability A given B, which is the same as PB given A, where PB is defined like this. So the probability, conditional probability itself is a probability measure. Right. Okay, so you now have seen several examples of probability measures. The classical probability measure that you can use if the sample space is finite and if the outcomes are equally likely. You can use the relative frequency measure if your experiment is repeatable. And then in that case, you can use Pn as a measure, but if n is large, then the probability that you get will be more accurate. Otherwise, it's just an estimate which may have a large error. right? So in addition to these definitions, we need some rules to calculate the probability of general events, because generally an event can be a very complicated function including intersection, union, complement, everything may be inside that event that we are interested in, right? For example, let me look at some kind of a circuit. For example, suppose you have a circuit like this. uh, right. Now I want to find out what is the probability. Suppose, for example, these are bulbs or something. Okay. Suppose I know the probability that bulb works, right? When you buy it from the shop, maybe only 95% of the bulbs are working, other 5% are not working. So I know the probability that any bulb will be working when I start using it is 0.95. ඒක මම දන්නවා probability of that the bulb is working. දැන් මෙතන මම ඒ වගේ bulb හතරක් පාවිච්චි කරනවා. So if I ask what is the probability, if I put my bulbs like that, what is the probability that the system will work, right? So how do I find out that? I know the probability that any bulb will work, right? But what I want is the probability that the system will work, right? So ඒ වගේ එකක් හදාගන්න ඒ හොයන්න නම් අපිට probability rules අවශ්‍යයි, right? අපි හිතමු let's write down some events. For example, say this I'll define W1 to be the event that the first bulb works, right? When you take from the shop, first bulb works. Let's say W2 is the event that the second bulb works. W3 is the event that the third bulb works. W4 is the event that the fourth bulb is working, right? So the probability of W1 will be 0.95. Probability of W2 will be 0.95. Probability of W3 is 0.95. This is also 0.95 probability. But what I am interested in, what is the probability that the system works? So W is the event that the system works. Right. එතකොට මේ ටික දැනගත්තට අපිට W වල සම්භාවිතය හොයන්න බෑ. W ලියා ගන්න වෙනවා අපිට. We have to write down W in terms of these things. And then we have to use some rules, probability rules, to calculate the probability. So that's why we need probability rules. So how can we write down W in terms of W1, W2, W3, W4? How can we write down W in terms of these ones? අපි දන්නවා අපිට මොකද්ද complement පාවිච්චි කරන්න පුළුවන්, intersection පාවිච්චි කරන්න පුළුවන්, union පාවිච්චි කරන්න පුළුවන්, right? ඒවා විතරයි අපිට those are the event operations. Events සඳහා පාවිච්චි කරන්න පුළුවන්. ඒ උපරි අපිට එකතු කරන්න බෑ, අඩු කරන්න බෑ events, right? So how can we write down W, where W is the event that the system works, in terms of W1, W2, W3 අපි හිතමු. Huh? Uh, not necessarily. Not necessarily. මේක අනිවාර්යෙන්ම වැඩ කරන්න එපා. අපි හිතමු කරන්ට් එක යනවා කියලා. මේක පිච්චිලා නම් සිස්ටම් වැඩ කරන්නේම නැහැ. මේක අනිවාර්යෙන්ම වැඩ කරනවා. ඊට පස්සේ මේ පැත්ත හෝ මේ පැත්ත වැඩ කරනකොට නැතිනේ කරන්ට් එක යනවනේ එහා පැත්තට. right? එතකොට එහෙනම් මේක සහ මේක හෝ මේක සහ මේ දෙකම වැඩ කරනවා. right? එතකොට අපිට ඕන නම් ලියන්න පුළුවන් මෙහෙම W is equal to W1 intersection W2 or W3 and W4, right? W1 and මේක අනිවාර්යයෙන්ම සිද්ධ වෙනවා. W1 and W2 ඒ කියන්නේ මම ගත්තොත් මේක එක සිස්ටම් එක system 1 and system 2 කියලා ගත්තොත් W1 and system 1, W1 and system 1 or system 2, right? So this is system 1 or system 2, right? Intersection is also and always. Union is O. Right. So W is equal to W1 and W2 O W system 1 O system 2. System 2 means this one and this one. System 2 එකට කරන්න මේ දෙකම වැඩ කරනවා. ඒකට ඒ විදිහට ලියන්න. So දැන් ඔහොම ලියාගත්තට පස්සේ අපිට දැන් අවශ්‍ය වෙන්නේ probability of this one. Right? එතකොට දැන් ඕක හොයන්න අපිට මේ නිකන් දැන් මොකද්ද කරන්නේ කොහොමද හොයන්නේ? We have to use the probability rules. මෙතන තියෙනවා සමහර events අපිට ගන්න පුළුවන් සමහර ඒවා independent events. Some events are mutually exclusive. Right? So there are some probability rules saying if two events are independent, then you can use this. Right? For example, we can easily find out the probability of intersection in that case. If two events are mutually exclusive, then you can find out the probability of the union. Right? So like that, there are rules. So we have to know those rules. So can you tell me whether you have heard about those rules? Anyone? Do you want me to go through those? So, huh? ගියර කවන්න නැද්ද? ස්ලයිඩ් එකේ මේ ටික තියෙනවා කොහොමවත් මම කියන්නේ එක්ස්ප්ලেইন කරන්න ඕනද කියලා අහන්න. Do you know what mutually exclusive events are? How do you define mutually exclusive? ඒක තමයි. වැරදි එක. ඒක වැරදිපු එක හොඳයි. දැන් වරදින එක තමයි හොඳ. හරියන එක නෙමෙයි හොඳ. වරදින එක තමයි හොඳ. මොකද මට පැහැදිලි කරන්න පුළුවන්නේ දැන්. මොකද ඕක හැමෝටම වෙනවා. හරි? ඕක පටල ගන්න හුඟක් අය. ඔය independence and mutually exclusiveness හුඟක් අයට පැටලෙනවා. දැන් ඔය කිව්වේ independence. matter වෙන්නේ නැහැ කියන්නේ independent depend වෙන්නේ නැහැ කියන එකනේ. ඒක වෙනස්. mutually exclusive කියලා කියන්නේ දෙකම එකවර වෙන්න බෑ කියන එක. Two events are mutually exclusive if both events cannot occur at the same time. Right? එකම experiment එකේදී දෙකම වෙලා තියෙන්න බෑ. අපි හිතමු අපි මේ කාසියක් නෑ අපි හිතමු මොකද්ද ඩයි එකක් රෝල් කරනවා කියලා we are rolling a die right වෙන්න පුළුවන් events තියෙනවනේ large number of events තියෙනවනේ එකක් තමයි ලැබෙන සංඛ්‍යාව ඔත්තේ වීම වෙන්න පුළුවන් event එකක් ඉරට්ටේ වීමත් වෙන්න පුළුවන් හැබැයි ওই දෙකම එකපාර වෙන්න පුළුවන්ද බෑ එහෙනම් ඔත්තේ වීම කියන event එකයි ඉරට්ටේ වීම කියන event එකයි දෙකත් they are mutually exclusive right ඒක ඉන්ඩිපෙන්ඩන්ස් නෙමෙයි. ඉන්ඩිපෙන්ඩන්ට් කියලා කියන්නේ එකක් සිදු වුණාද නැද්ද කියන එක මත නදාපවතින්නේ නැහැ. අනික සිදු වෙනවද නැද්ද කියන එක. ඒක probability ආශ්‍රයෙන් කිව්වොත් probability of happening one event doesn't change if we know the probability that the other event has happened. Right? අර අනික් event එක සිදු වෙලාද නැද්ද කියලා අපි දන්න වෙලාවට දැනගත්තත් නැතත් අනිත් event එකේ සම්භාවිතාව වෙනස් වෙන්නේ නැත්නම් ඔන්න independent. ඒක mathematically කියනවා නම් suppose you have two events if the probability of one event say for example A is the same as the probability of A given B දැන් අර මේ දැන් කියපු ඔය දෙක සමාන නම් ඒ කියන්නේ මොකක්ද එහෙනම් A and B are independent right probability of A කියන එකට යම් කිසි අගයක් තියෙනවා අපිට ඕන නම් probability of A හොයන්න පුළුවන් B සිදු වෙලා තියෙනවා කියලා අපිට කවුරු හරි කියලා තියෙනකොට නැත්නම් if එහෙම වුණොත් කියලා උපකල්පනය කරනවා. එතකොට A probability එකත් අපිට හොයන්න පුළුවන්. A දෙකම හැබැයි සමාන නම් ඒ කියන්නේ මොකද්ද? B සිදු වෙලා තිබුණත් නැත්නම් A වල සම්භාවිතාව වෙනස් වෙන්නේ නැහැ. Right? So that means they are independent events. So that's how you define independent events. එතකොට මේ දෙක පටල ගන්න එපා. Mutually exclusive and independence. Right. So here I have just listed the probability rules that we have to use. Actually, these are the only probability rules. There are a couple of more that we have to use. Using these, we can find out the probability of any complex event generally. Once we know some of the probabilities, right? So, complement rule says probability of some event not occurring. A complement is not occurring A is equal to 1 minus the probability of occurring A. Right? So that is called the complement rule. And addition rule we use to find out the probability of a union of two events. Probability of A union B is equal to probability of A plus probability of B minus the probability of the intersection. That is the general case, always correct. But there's a special case if A and B are mutually exclusive. A and B cannot occur, therefore the probability will be 0 and therefore this part will disappear. Right? So therefore if A and B are mutually exclusive, then this is the formula that you can use. And then the multiplication rule is used to find out the probability of an intersection. Right? So generally, we can define it to be like this: probability of A intersection B is equal to probability of A given B. මම තාමත් මෙතනදී අර කලින් original notation එක පාවිච්චි කරේ. Probability of A given B times probability of B. එහෙම නැත්නම් probability of B given A times probability of A. That's how you define it. If you write down in the usual notation, it's like this: probability of A intersection B, probability of A given B times probability of B, and so on. But if A and B are independent, then just I mentioned that this probability is the same as the probability of A. Right? If A and B are independent, probability of A given B will be the same as probability of A. So therefore, you can replace this as probability of A, then you get probability of A intersection B is equal to probability of A times probability of B. Right. Then law of total probability, a little bit of mathematics, therefore let me show it using a graph here. Suppose you have a sample space and suppose you have several events, say for example A1, A2, A3, A4, A5, which are mutually exclusive and exhaustive. Right? For this to be valid, we should have some events A1, A2, A3 and so on, mutually exclusive and exhaustive. So now you know what you mean by exclusive. That means there is no intersection. What do you mean by exhaustive? Exhaustive means the union of the events is equal to the sample space. That's what you mean by exhaustive. So suppose you have another event B and you are interested in the probability of B. Right. So suppose you know the probability of happening B, you don't know the unconditional probability, but you know A1 සිදු වුණොත් B සිදුවීමේ සම්භාවිතාවය අපි දන්නවා. එහෙම නැත්නම් අපිට හොයාගන්න ලේසි. Right? A2 සිදු වුණොත් B වල සිදුවීමේ සම්භාවිතාවය හොයාගන්න ලේසි. ආදී වශයෙන් suppose we know, or it is easy for us to find out the probability of B given A1, given A2, given A3 ආදී වශයෙන් ඒ ටික දන්නවා නම් නැත්නම් ඒක හොයාගන්න ලේසි නම් එතකොට අපිට total probability law එක පාවිච්චි කරන්න පුළුවන්. So in that case probability of B is equal to probability of මෙතනදී මම අනිත් පැත්තට අරන් තියෙන්නේ A1 A2 right. A කියලා ඉවෙන්ට් එකක් කරන් තියෙනවා, අනිත් එක B1 B2 කියලා අරන් තියෙන රූපය. So B1 B2 B3. Suppose you have several events B1 B2 B3 and so on, mutually exclusive and exhaustive. You are interested in event A, right? So what you are interested in is the probability of A. Right? So probability of A can be written in terms of the conditional probability of A given B values times the probability of B's. So the B වල probabilities ටික දැනගන්න ඕනේ. අර වෙන වෙනම තියෙන mutually exclusive probability ටික දන්නවා නම් සහ conditional probability of A given those events are known, then you can use this. Right? So ඒක තමයි total probability law කියලා කියන්නේ. එතකොට ඒ වගේම last එක Bayes theorem. දැන් මේවා ඔක්කොම A level වලත් මම හිතන්නේ කරලා ඇති. I think that you have done it in A level. So when do you use the Bayes theorem? Bayes theorem, in order to apply Bayes theorem, also we should have this kind of situation. Okay? Several mutually exclusive and exhaustive events and another event, for example, B or A whatever. And then make a පාවිච්චි කරන කොයිලාවටද? අපි අර probability of මෙතන හැටියට නම් B given A1, probability of B given A2, probability of B given A3 ඒ ටික දන්නවා සහ probability of A1 A2 A3 ඒ ටිකක් දන්නවා. අපිට හොයාගන්න ඕනේ probability of A given B. B1 probability of A given B2 ආදී වශයෙන් හොයාගන්න ඕන නම් දැන් මේ වගේ අනිත් පැත්ත conditional probability එක හොයාගන්න ඕන නම් අපි use කරන්නේ Bayes theorem. එක පැත්තකට conditional probabilities අපි දන්නවා ඒකේ අනිත් පැත්ත conditional එක හොයාගන්න ඕන නම් Bayes theorem එක පාවිච්චි කරන්න පුළුවන්. So those are the rules that we use usually to find out probabilities. So ඒක ඔයා අපේ මේ දෙමිඩියන්කෝ පොතේ නැහැ. නමුත් අපිට මේව නැතුව කතා කරන්න බෑ. ඒ නිසා I included that as a basis here. Right. Okay. So next topic is a random variable. That's where almost the Davydenko book starts. But I think it's a good place to take a short break. Right. So we'll start.